In this video, I want to take a look at the procedure in partial fractions for what you do when you've got an unfactorable quadratic factor in your denominator. So I want to just illustrate it by doing this integral here. I should point out that on an integral like this, I notice it's polynomial divided by polynomial, so I got partial fractions in mind. But I also have u substitution in mind, because usually the simplest thing to do is u substitution. And with a cubic in the denominator and a quadratic in the numerator, I'm thinking, whoa, what if I let the denominator be u? Then maybe du is that numerator, and this might just be a really simple log or something like that that we would integrate. However, the denominator, if u is equal to the denominator, then du would have to be 6x squared plus 2, and this is not just a scalar multiple of 6x squared plus 2. It's got an x in it, and yeah, so that's not going to work. So okay, I'm going to go to partial fractions. First thing I'm going to do is factor the denominator. So I'm just going to look at this 5x squared plus 4x plus 3. I factor that denominator. I notice I can factor 2x out of it. So then I'm left with an x squared plus 1. Okay. And that x squared plus 1, it turns out, is not factorable with real coefficients. If you look at the graph of it, this is y equals x squared shifted up 1, so it doesn't hit the x-axis anywhere. So it doesn't have x-intercepts, and hence it doesn't factor into real components. If you allowed for imaginary numbers, then you could factor it into x plus I and x minus I, but let's not go there yet. So what I'm going to do is I'm going to split this up. I do have one linear factor there, 2x, so we're going to stick that as an a. And then I've got this unfactorable quadratic. Well, I have to just leave it as it is, but what I put above it is going to be a linear thing, so bx plus c. If I could factor it, I'd have two linear things, both with constants. And if I got those two linear things back together again, I'd have a quadratic denominator with a linear numerator, so that's what I go with. I just go with that linear numerator over the quadratic. Okay. So now, doing the same kind of stuff as we've done before, you multiply both sides by this denominator, so that you just end up with a numerator on this side. 5x squared plus 4x plus 3 equals this denominator times the first fraction. The two x's cancel out, so I'm left with a times x squared plus 1. And this times the second fraction, the x squared plus 1's cancel out, and I've got 2x times bx plus c. Okay. Now I got to solve for a, b, and c. One thing I don't think I've mentioned before, but I want to mention it now. One of the things I can check when I'm setting this up to make sure I've got it right, particularly as the denominators get bigger and bigger power, but whatever the power is in the denominator, this is 3, this is a cubic polynomial, tells me how many variables I should be looking for. This is cubic, I should be looking for a, b, and c, 3 variables, right? Power 3, 3 variables. If it was power 7, I'd end up with 7 variables there somewhere. It's just an easy double check to make sure that you at least have a chance of having it set up right. If this was 3 and I had 4 variables here, a, b, c, and d, something's wrong. Or if I only had 2 variables, then something's wrong. I've got a cubic, I'm looking for 3 things there. So, how am I going to do this? I'm going to pick some values for x. So let x equal, I think 0 would be a good one. Let x equal 0. So on this side I just get a 3. And on this side, I get a times 0 squared plus 1 is 1, plus 0 right there. And that tells me that a equals 3. Good. Let's pick something else. Now, generally, I'm picking values for my variable that makes, I picked a 0 so that this one would go to 0. Generally, I'm picking those values, but I don't have one for the x squared plus 1. I have to plug in I or minus I. That's weird. So at this point, you're just picking any number. If I hadn't already used 0, I would try using 0, because plugging a 0, and if this factor was something different than just an x, it was like an x minus 1, then x equals 0 would go in there, and the b would go away. That's what's nice generally, is if one or two of the variables goes away, and you can just solve for the other one. But I think in this case, I just got to bite the bullet and see what I get here. So I'm going to plug in x equals 1. So the right-hand side is 5 plus 4 plus 3. That's the left-hand side, actually. The right-hand side is a, but I've already solved for a. That's 3 times 1 plus 1. Well, 1 squared plus 1, but plus 2 times 1 times b times 1 plus c. So it looks like, let's see, I'm going to take this, actually this is through 6. I'm going to pull the 6 over here. So I've got 9, 12. 12 minus 6 is 6 on this side. And I've got 2b plus 2c. And one more. Pick anything you want. I'm going to pick minus 1. So I've got 5 minus 4 plus 3 equals a, but I don't know what a is. That's 3. Negative 1 squared is 1, plus 1 is 2, plus 2 times negative 1. Now plugging in a negative 1 for x, I've got a minus b plus c. So again, this 6 right here, I'm going to subtract over to the other side. So I've got 1 plus 3 is 4. 1 plus 3 is 4. Subtract 6 is negative 2. Equals, when I distribute the negative 2 in here, I've got minus, no, the minus minus becomes a plus, 2b minus 2c. Okay, so I know what a is. I've already got that one. Now I've got two equations here, this one and this one, which I can solve simultaneously to figure out what b and c are. In fact, I can see that if I just add the two equations together, that'll be nice. So the 6 plus the negative 2 is 4. The 2b plus c and the 2b minus 2c, the 2c's go away, and I've just got 4b, which tells me that b is equal to 1. And then use either one of those equations. Let's just go up here and say 6 equals 2 times 1 plus 2c. So subtract the 2, 4 equals 2c, and c is equal to 2. And I have to admit that sometimes I plan out my examples, and sometimes I just make them up on the spot. And generally, if I make them up on the spot, I get really weird fractions for answers. I really lucked out this time because I honestly made this one up on the spot. I said, let's just write down one and see how it goes. I knew what am I lying to you? No, I'm lying to you. I did plan this one out. I just looked over at my notes. Huh. Okay. Well, good. They came out. So what does that tell me? I was splitting it up this way. So I've got a over 2x. So a was equal to 3. So I'm looking at 3 over 2x plus, this is an x squared plus 1 here. And then it was bx plus c. So b is 1, x plus c is 2. So I'm looking at the integral of that. My original integral was the original of that one function, and that function breaks up into these two, the sum of these two functions. And now I can integrate these individually. This one is just going to be 3/2 times the natural log of the absolute value of x. But now I got to figure out how to do this integral. And generally what happens on these things is you can break them up. So for instance, if I write this as x over x squared plus 1 plus 2 over x squared plus 1, then this one works with a u substitution because you do u equals x squared plus 1, so du is 2x dx, and so I'm missing a 2, so put a half out in front of that. This ends up being 1/2 the natural log of x squared plus 1. Notice I don't worry about the absolute value sign because x squared plus 1 is always positive. So I've still got that stuff. And then this one right here, well, this one right here is an arctangent. 2 times the arctan of x plus c. If you've got that unfactorable quadratic, you're going to write it down with a linear numerator. It may turn out, sometimes what happens is like when I'm solving for b here, where did I solve for b? Right, I solved for b. That might turn out to be 0, in which case this would have been 0x plus 2, and you wouldn't have had a linear piece there. But you have to assume that it might be linear, that this might have a coefficient in front of the x other than 0. But take it what you get. Then generally what happens is you got to split it up. You got to see what the derivative of this bottom is and use that as the numerator, and then take the other stuff and you do a distributive property. Right? It might be a little bit different each time depending on whether this has an x term in it or it's just an x squared plus 1 like this one is. Anyway, the process is the same in that you need that linear over that unfactorable quadratic. What you do for the integral depends on what's there. Right? Sometimes you might have to complete a square. This already is a completed sum of 2 squares, so it worked pretty well. Anyway, there's the procedures for partial fractions. You should try a bunch of these now.